Do you know the differences in the occurrence of earthquakes in Californian region and Himalayas? In California, the earthquakes are basically strike-slip type of faulting, and in Himalayas it is the thrusting type of fault. The basic difference between strike-slip fault and thrust fault is the motion of the fault plane in strike direction and in the dip direction. To know the difference of the physics of the earthquake, we do the focal mechanism studies. These studies are one of the important part of seismology, in which we study the fault planes, and the tool used for that is the fault plane solutions. The elastic rebound theory given by Reed in 1910 is commonly accepted as how the earthquakes are occurring. According to this theory, the earthquakes they occur in the regions where the deformations are going on. For some time, the strain energy is accumulated in a region which is deforming, and then this strain energy is released when it exceeds the strength of the rock. So, it is clear that the faulting, according to this theory, is the cause of the earthquake. And once we accept that the faulting is the cause of earthquake, then we can also find out what type of fault it was which has given rise to this earthquake. Nakanos in 1923 investigated the propagation of seismic waves theoretically and found that the system of forces which are generating these earthquakes are like single couple forces. Now, if they are single couple forces, then they should generate the compressions and dilatations in the quadrants which are orthogonal to each other. Encouraged by Nakanos, Barely in 1926 investigated the first P wave motion of the seismograms recorded by the earthquakes. He found that the first motion, which is either compression or dilatation, can be used to infer about the fault system, which is the source for the earthquake occurrence. To estimate the fault type and how the earthquake has generated, the first P wave motion can be used. Therefore, it is necessary to trace back this first motion to the hypothetical focal sphere. This focal sphere is a three-dimensional sphere, and it is necessary to change this three-dimensional to two-dimension, for which we require projection systems. Before we know the fault plane solutions, it is necessary that we know the type of faulting. If we see this figure, there are three quantities which are explaining the orientation of the fault plane. The strike is the line in horizontal plane, while the dip is measured in the vertical plane. The slip angle is the angle which the fault plane is making on its own plane in the direction of slip. Based on these three quantities, the fault types are categorized as two types: the dip slip and the strike slip. The strike slips are those faults in which the slip is taking place along the strike, while the dip slip are those faults in which the slip is taking place in the dip direction. If we see this figure, in this, the two types of strike slip faults are given. One is left lateral strike slip fault and another is right lateral strike slip fault. The dip slip faults are again categorized into two types. One is normal faulting and another is thrust type of faulting. In normal faulting, the hanging wall goes down, while in reverse type of faulting, the hanging wall goes up. Now, how to know which type of mechanism has taken place during the occurrence of earthquake? Now, in this topic, we will explain what is fault plane solutions, which are the important tools to find the physics of the source. We will learn how to make fault plane solutions and then how to interpret them in terms of physics of the source. Before we go for fault plane solutions, let us see how to project the three-dimensional things to two-dimensional, because it is not easy to plot the fault geometry in 3 dimension, and to plot it on 2 dimension we need some projection systems. The projection system which is usually used in seismology are of two types. One is equal area projection system, in which the area is conserved, while the other system is equal angle projection system, in which angle is conserved. The equal area projection is also known as Lambert or Schmidt projection. In equal area projection, if we place a sphere on the horizontal surface, then the point A can be projected as point B on the surface, where A is on the circumference of the sphere and B is on the inside a circle, while the equal angle projection is known as stereographic or Wolf projection, and this is the projection which is most of the time used in seismology. In this, the point C is projected as point D in the middle of the sphere, joining the zenith of the sphere at the top of this. Let us see how these projection systems look like on a globe. In this, we have detached 1/4 part of the globe. The meridional net is basically representing the equal area projection, while the polar net is representing the equal angle projection. We will learn now how to make the great circles for the equal angle projection, which is used in seismology. For making these lines or the great circles in 2 dimension, we divide the circumference of the circle into 360 degrees. The 20 degree at the outer point makes 10 degree at the center. We take the point at the 10 degree and join it at the top of the circle to take a radius and make a chord inside this circle. This becomes the great circle of 10 degrees. Then we go on increasing it and find that the 90 degree angle is at the center of this, and the 0 degree falls at the periphery of this circle. This gives basically the angle of the plane, which we will learn in the next figure. Before that, let us also see how to construct the small circles. For the small circles, similarly we divide the circumference into 360 degrees and then make tangents from same angles on both sides of the circle. Let us take the example of 10 degrees. If we make the tangents from 10 degrees and join it at the center line, then that line becomes the radius of the 10 degree small circle. Similarly, we can make the small circles for all the angles. If we join both of them, then we get the stereographic net ready for use for the fault plane solutions. Now, let us see how a plane looks like on the stereographic net. The net, which is shown here, is giving the azimuthal angle at the periphery, represented by the smaller circles, and the great circles, they are giving you the dip of the plane. So, a plane with 90-degree dip in the north direction will look like a straight line as shown in this figure. Let us try to construct a plane of 90-degree dip in north-south direction. This will be a north-south strike plane with 90-degree dip. Now, the second plane which we will construct will be a 60-degree dip in north 45-degree azimuthal direction. For this, first we construct the 60-degree dip as shown in the figure, and then we rotate the plane in north 45-degree and then make a line there. So, this plane is now showing a plane having north 45-degree strike and a 60-degree dip. These planes, they are representative of the fault planes in earthquake source. Now, let us try to construct two planes which are perpendicular to each other. For the first plane, we have just learned how to construct it on the stereographic net. Now, the second plane, which is perpendicular to it, will be constructed by putting a node point 90-degree to the first plane. This node can be found by placing the direction of the plane in north-south and then counting 90 degrees away from this on the stereographic net. That becomes the pole point of this plane. The second plane, which is orthogonal to this, has to pass through this pole point, so that it is perpendicular to the present one. These planes, wherever they cut each other, that point is called as null point. After constructing the planes, now we will learn how to plot a point with a particular azimuthal direction and a takeoff angle. The azimuthal direction is similar to the strike direction in case of plane, and the takeoff angle is similar to the dip direction. First, we plot the strike direction and then the dip direction. In this case, the 60-degree is the strike direction, while the 30-degree is the takeoff angle for this particular point. Similarly, the strike direction 60-degree and 40-degree takeoff angle is plotted in this figure. We have seen how to change over from 3-dimensional to 2-dimensional figures. Also, we have seen that the P wave first motion can be used to find the fault plane solutions. Now, let us see how it works. First, we take all the seismograms recorded by the earthquake and then mark the first P arrival with compression or dilatation as shown in this figure. The up motion is the compression, while the down motion is the dilatation. There are different practices for doing this. Some use up or down, that is U or D on the focal sphere while plotting the data. Some may use the dilatation or compression, and sometimes the compressional part is blackened in focal mechanism studies. After finding the first P wave motion and earmarking it as up or down or compression or dilatation, it is marked on the focal sphere. Now, to change it to the focal sphere, the spherical coordinates are changed to polar coordinates. Let us take a point r alpha beta on the focal sphere. R is the radius of the focal sphere, alpha is the azimuthal angle, while beta is the takeoff angle. Now, to transform it to two-dimensional figure, we transform these coordinates to plane polar coordinates r theta, where r is given by 2r sin beta by 2 and theta is alpha. Generally, the radius of the hemisphere is considered as unity, and therefore, r becomes under root 2 sin beta by 2 and theta remains as alpha. There are two types of practices used for representing the focal sphere. Some of us we use lower hemisphere, while others they use upper hemisphere. And since most of the waves from the source goes down, so most of the time the seismologists they use the lower hemisphere. Now, to take into account the upcoming waves when the beta becomes more than 90 degree, we make corrections in alpha as alpha equal to 180 degree minus alpha, while beta becomes beta equal to 180 degree minus beta. We plot these points on the lower hemisphere and project them on the stereographic net. After plotting these points on the stereographic net, we take help of great circles which divide the compressions and dilatations. We first divide the compression and dilatation using one plane, and then we take another plane which is orthogonal to it, that is 90 degrees to this, and then again divide the compressions and dilatations. One of the examples is shown in this figure, where two planes are shown as WBCE and FBAG. In this, we are considering one of the orthogonal planes, that is the nodal plane, as the fault plane, and the other is called the auxiliary plane. This is the data from one of the earthquakes, and after plotting it on the hemisphere and dividing it by the great circles, we have found the geometry of the fault like this. The fault plane, which is generally chosen based on the geology or the prevailing tectonics of the area, is strike north 90 degree east and dip 44 degree north, while the auxiliary plane in this is strike north 54 degree west and dip 52 degree southwest. From this figure, we can find the slip vector also. Slip shows the slipping of one wall, whether it is hanging or footwall, on the other on the fault plane. This slip vector in this case is strike north 36 degree east and the plunge is 38 degree. In this episode, we have learned what is fault plane solution, how we make fault plane solutions, and how we interpret them for the focal mechanism studies. Now, do you know what is the strike direction and the dip direction for the Bhuj earthquake, which occurred on 26 January 2001? The fault plane solutions are always given along with the size and location of the earthquake. You can find them with the solutions of the earthquakes appearing in most of the seismological bulletins. Most of the earthquakes which are occurring in Himalayas are thrust type, in which one of the fault planes is having the dip lesser than 10 degrees, because the thrust type are those fault types in which the dip is less than 10 degrees and they are reverse. Similarly, do you know what was the fault plane solutions given for Sumatra earthquake? These give you the idea about the geometry and the physics of the source of the earthquake. This was one of the important aspects of seismology. We will be discussing other aspects in next episodes.